Is everybody is here? Is this getting broadcasted now?
Yep, it is.
Hi, everybody. Good morning. Today we are going to go over the calculus and linear algebra for machine learning. And we're going to look at various topics covering today. We'll be covering backpropagation in neural networks. And as I mentioned earlier, that if you guys have either Anaconda Jupyter or Google Colab set up on your computer, then you should be able to run some code as well. And you can practice while we were going through the mathematical concepts and the architectures of neural networks. We can go through that. So that's the goal for today. And so today we're gonna look at these topics, and also like if you would like to get in-depth information and thorough analysis of these topics, you can also gain insights through the book so that you would get more answers. And if at any time at all you have any questions, just feel free to ask these questions through the chat window we have, and I will be able to answer you as well. So basically, this is just a brief background of the experience, and we'll get started. So before we get started, I'm just going to give you a little bit of a background of, as we all know that there are several branches for data science, and so the data science has like data engineering, and then you have ML engineer, you have deep learning engineer, and even in data engineering itself, you have data modelers, data architects, and then you have statisticians that will be working on building some algorithms. So there are several areas and branches of machine learning and deep science that apply to the field. And so basically, based on where you are, you could potentially leverage your experience, and you can apply to this field of machine learning and deep learning. So let's say that you're working as a data analyst and you would like to be a data architect, then yes, there is a career path for that as well. And let's say that you are getting started into the field of data science and you would like to understand the concepts and you would like to be an ML engineer or deep learning engineer, yes, then you could also, in any case, for if you are especially going for machine learning or deep learning, then you would need the fundamental concepts of calculus and linear algebra that will basically help you to be able to, build some foundational background before we can, because everything we see here, whether we're talking about neural networks or we're talking about like a singular value decomposition or any other applications of machine learning and deep learning, you will have basically, applications of mathematics that we need to, apply practically in order to be able to achieve the results that we are looking for. And again, it could be any industry. You're talking about retail, life sciences, or healthcare, utilities, energy, chemicals, FDA-approved companies, any companies that you're working for, or you're building your career roadmap to work for these companies. It's essential that we have these fundamental concepts established so that we'll be able to implement that for the customer that we'll be working for. So before we get started, I'll just give a brief background of where we are with the artificial intelligence and machine learning. So as we all know that machine learning is not a new concept that we are having today. Machine learning has been there for a long time. And so all of these years that there has been a lot of rapid advancements in the field of machine learning and deep learning. You start with like Bayesian neural networks, and then there were just neural networks. And then there were a various number of algorithms like the naive Bayes algorithm, and then you have linear regression algorithm, you have linear logistic regression algorithms. A number of algorithms have been implemented, and then for coming to like toward the 80s, you might be seeing most of Bayesian neural networks, and then toward the 70s, you should see mostly like the neural networks implementations and the rise of the reinforcement learning as well. So there are a lot of applications for robotics have begun in 70s as well, so that you can see like how it can be implemented. And as we continue to push forward and push the envelope of this machine learning and deep learning, that we continue to build some advanced neural networks. So in 2012, we hear the term called deep neural networks. And deep neural networks is where it's not like we are just limited by few neural networks that we are building a particular application. We can build any number of neural networks, thousands and thousands of neural networks, especially if you are working for high performance computing applications, or you're working in a supercomputing lab where you would need to build a trajectory of plasma or something else. All of that you can accomplish by building any number of neural networks, which is what a lot of people and practitioners in the industry currently have been implementing these type of applications that will actually help them to be able to build any advanced algorithm that can crunch all of the information, and then instead of like processing it for years and years with the classical computer logic, then we are able to process them like in minutes now. So that's where the advancements have come up. And all of this is again, like there have been, the Python has been there from 90s, but then recently we also see TensorFlow that began few years ago, and then we also see the advent of PyTorch few years ago as well. So the reason why the TensorFlow and PyTorch have been brought up as opposed to leveraging the bare Python or bare NumPy algorithms is because primarily the way that we are implementing this is like if you are to code in Python, that there's a lot of manual computation and mathematical computations you have to code yourself, because it is not having a lot of packages, because that's the way that it was built in the earlier stages of the build. And so what happens is like when you are going for advanced calculations, there's a lot of packages that are not there. But coming to TensorFlow and coming to PyTorch, you are able to apply that. Because there are a number of packages, for example, AutoDiff, like which is for the auto differentiation of calculus. There are a lot of packages that are available, and for tensors, you have a number of packages available, even built-in functions that you can invoke, and you're able to perform large-scale computations with TensorFlow and PyTorch. And apart from that, there are also you can just run them on any GPUs, and it will improve the scalability of the performance of the overall computation of the tensor calculations. So that is another advantage if you're going for TensorFlow or PyTorch. Of course, you may ask me, why can't we run GPUs on Python instead of running on the CPU? Yes, you can, but then it will require a lot of manual wrapping operations that you need to write to say, okay, attach this CUDA device and start this and start that and wrap the whole unit into running a GPU unit, and then you will be able to compute and so on and so forth. So that's where you have a lot of advantages in PyTorch and TensorFlow as opposed to Python. But for this particular example, we're going to still look at Python, because the reason is that you will be able to understand the concepts of what we are applying here, so that it will be we basically we're going to start preparing, writing up this on a paper, and then we go into actual implementation in Python, so that we know in advance what we are trying to, what is our goal here, what are we trying to accomplish, and how we are going to accomplish, and then we're going to go and execute that. So that's what we're going to look at today. And also I'll be showing you singular value decomposition, which we call is a $1 billion algorithm. The reason why we call it as a $1 billion algorithm is because number of companies like Amazon or I'll come to that when we will come to that topic. I'll show you why and how we can implement it and what are all the benefits of implementing that particular algorithm. So again, so basically, as I told that, there have been a lot of advancements on the neural networks and a number of algorithms. And again, the foundation for all of these algorithms is coming from the statistics field. So you will be able to get all of that from my book, every single algorithm from the statistical field, and see the math behind each algorithm. And then you can also see the implementation of that algorithm as well. So we'll have a whole lot of every single algorithm has been covered, so that you will not be requiring to refer to a lot of books. You can just go through the same book for all the applications of machine learning and deep learning algorithms, and you should be able to see the implementations as well, so that you can run some practicing sessions by executing that either in the Jupyter Notebook or through the Google Colab. But that's what the thing is. So I think somebody has a question here. Let's see what's going on. The slide is frozen. Okay, is this what slide are we seeing now? Are we not able to see the slide now? It's working now. Okay, great, awesome. Okay, so we'll just go back to the earlier slide here. So here is what I was just going through here, and as we can see, so this is a simple neural network, and so in this neural network, we are able to basically, run through the a simple neural network here. We have A1 and A2 as the input neurons, and then we have like Y1 and Y2 as the processing neurons, and then you will get the output as the Z1 and Z2 neurons from there. So, and again, each node of this neuron is connected to the other node in several ways, as we can see here. And also, each neuron is assigned with a weight. The weight is what we are going to initialize and then sum it up later. So we will see how we will compute that and sum it up later. But basically, this is what we have. So this is basically the is a basic neural network. And so again, the neural networks, as I told, like the advancements have been very vast in the recent times. It has been implemented for various fields such as genomics or chemical industries, and so on and so forth, even autonomous cars, speech and natural language processing, neural machine translation, and so on and so forth. So all of these applications have been successfully implemented, including the building some deep learning models to discover new drugs and understand the causes for the diseases as well. So to take the deep learning to the next level, so we need to see how we can understand these various types of neural networks. Like we're talking about convolutional neural networks, so we're talking about the recurrent neural networks and restricted Boltzmann machines, so on and so forth. Okay, we have a question here. Name of the book. Okay, the name of the book is primarily it's a greater foundation for machine learning. So that's the name of the book, and you can find that in Amazon. And also a lot of these things I'm talking about right now, also you can find as articles as well, so that you can actually. So for example, so if you how are you going to be able, because this is the book, and how would you like to activate these neurons, right? So we need to activate each neuron. So you can also refer to my articles as well. So I put the code and sample examples so that you can execute this and understand each activation function and how we can activate. Similarly, I'll put all the articles so that you can just reference these articles and you can, basically go through that. And that way you can cover a lot of topics. But today we're going to go through the whole neural networks. So I think I answered the question, right? I just gave the reference of the book. Also, I'll just, so here is the name of the book, just in case you would like to refer. So this is the book here. So we are good, right? Okay. So yeah, so I'm just basically going through this neural networks here, and I just showed an example of how to, you know, yeah. Okay, so basically, I was just showing how we are going to put the assign the weights here, and then we are able to apply to a number of industries as well. So that's what I was just referring to just now. And there are also, like, when we build this, we need to also perform some forward propagation and backward propagation of the algorithms, especially when we are training on large scale neural networks. So we can get the high accuracy in terms of the training and getting the results from the particular algorithm that we are applying. So hence it is very essential that we have a very high accurate result from the algorithm. So so that's what we are talking about here. And so Verbose is a person who actually has laid a foundation for training the neural networks. That was somewhere in 70s, and implementation of the such algorithm will give us, like, again, there are various types of hardware at that time that they were leveraging, but now we have more advanced hardware that we can leverage on infrastructure that we can compute this. So that way, like, that's what we are saying, that we want to apply. And genomics was like a project that was started, like, it literally ran like for 10 years. And then we are able to find out all the basic genomics and our understanding of modeling of pairs of DNA and everything. And we are able to, that took like literally a decade to get that, but now if you're able to apply, like if somebody wants to find out the DNA, it's going to be like, it's going to be so quick that we could just get the results like in minutes instead of getting the results in like years and years. So those are the advancements we are talking about, how the leveraging the large scale hardware that we can implement here. So we're going to look at the mechanics of the back propagation now and see how we can leverage this. So we have another question. Okay, so okay, I think I'm going to write it here. Okay, so that's the name of the book, and you can find it. And also a lot of articles also you can find on Medium. Is basically a place where you can find all these articles there. So you can refer to a lot of articles, and for the whole comprehensive coverage, you can refer to the book. But if it meets what you're looking for from the article itself, then probably you will not be required to look into the book because you already have answer to your question from there. So based on what you're looking for, you should be able to explore and see if you find your answers there. So again, as I told earlier, so basically, like, we could implement this in PyTorch or Python, or even we can implement this in TensorFlow as well. And so here we're going to initially architect this and come up with an architecture of how we're going to implement this in actual Python programming language. And then we'll implement it. But before we implement it, we want to know what type of neural network we are handling and what is that we are trying to achieve here. So all of that we are going to go through now. So basically, our goal here is to compute the backpropagation algorithm. And for that, we are creating the neural network. You can simply create this on a paper. You can just write it up and create a couple of input neurons, and then you create your processing neurons, and then these are the output neurons. So we can just build like that. And also we'll just add a couple of bias nodes as well. So this will actually reduce the bias in the overall computation of the accuracy of the algorithm. And you should be able to get accurate results with that. And here we're just initializing this weights of these neurons. So these are the weights we are initializing. Each weight we are given a name to it, and then we are just initializing some numbers. So this initialization, just calling a function, it will initialize all of that. But I'm just showing here, these are the initializing weights that we're going to assign so that we know what weights we're going to have here. And so basically, so these are all the weights we have. And so we initialize them, and we also have initialized weights for the bias nodes as well. And so the purpose of performing the backpropagation is to optimize the weights. And then we're going to take a forward pass to compute the total input assigned to each neuron and apply the logistic function. So again, I just showed activation functions. There are several functions that are available, and you can apply any of those, not necessarily logistic function. But for this purpose, I'm just going to be applying the logistic activation function. But you can apply, any other activation function. You can apply hyperbolic tangent function or tan activation function, or you can apply ReLU, rectifier linear activation function, or you can also apply leaky ReLU activation function as well. And then you also have a parameterized ReLU activation function. And also in the recent times, there's another activation function that's released called swish activation function. You can also apply a swish activation function if you would like to. But again, for this, simple purposes, I'm just going to apply the actual logistic function here. So, and then we can compute the how we can go about it. So logistic function, just refer to here to see, so this is the logistic function, and is also known as the sigmoid function. And so you can simply activate the neuron, and then it will come with a linear transformation. And the hidden layer or the processing layer we are talking about contains the weights that it's going to basically process this. And the sigmoid function performs a nonlinear transformation. So basically, this is 1 by 1 plus e to the power of minus z. So that's the formula for our logistic function. That is all we need to know for now. How it works and all that, we can refer to this article and see a sample example I implemented in PyTorch. But and also, like, what is the range of the numbers you can accommodate, and what is the output you're going to have. So all of that you can check here. But for now, let's say that I'm going to activate the logistic function to compute the net input y1. So basically, I'm going to initially compute the net input y1, so which is the hidden layer, or also known as a processing layer. So here we're going to compute the weight 1 multiplied by a1 plus weight 2 multiplied by a2 plus bias. This is the bias node we have multiplied by 1. So we just take the weights of each of these particular nodes, and then we also have some weights associated to the actual node itself. Like, for example, this neuron has here we have assigned some weights for this 1, 1, so 0.9 and so on and so forth. So we're just going to compute the net input y1, and then we're going to similarly compute the net input y2 here. So we have now the net input y2 computed. Now we're going to take this logistic function as an activation function. We're going to apply and then see. So basically, so this is a differentiation of error total by differentiation of weight 1 is differentiation of error total by differentiation of out y1 multiplied by differentiation of out y1 by net y1 multiplied by differentiation of net y1 by weight y1. So if we sum it up, so basically it would be a differentiation of error z1 by differentiation of out y1 plus differentiation of error z2 by differentiation of out. That will be actually y2. So here we have computed the net input y1. So now we're going to compute the net input y2. So this is the value we obtained for this. Now we're going to go and compute the output processing neurons, which are the Z1 and Z2. So we're going to compute the input for those, and that will be the weight of that multiplied by net output A1, which we already computed earlier. and then the W8 of net output. So that gives us the net input for Z2. And now this is where we're gonna take this value we computed for the net input Z2, and then we apply the logistic function, which is 1 by 1 plus e to the power of Z2. So that's basically 1 by 1 plus e to the power of this particular whole combination that we just got from the net input 2. So that will give us the net output of the Z2. So now we're going to compute the basically calculation process for the total error here. And so that's going to be the error of total equal to sigma 1 by 2 ideal target of actual output to the square. So that gives us the error net total. So this is a error we need to reduce and minimize it so that we can have a highly accurate result from the neural network. So here we're going to apply a chain rule. So chain rule is basically a very simple calculus mathematics here. So for this, it's function of a function. So in calculus, a chain rule is applied to differentiate a function of a function. So for example, we're trying to find the value of a cosine Z2. And then in contrast to finding the cosine function of Z, cosine Z2 is finding the cosine value of Z2. Let's consider these two functions as fz and zz, then we can represent as x of f zz. So here is a function of a function. So f of z is cos z of z, f z of z is f z squared is cos z. So this is called a function of function. So we're going to apply the chain rule here, which is differentiation of x by dz equal to dx by dy multiplied by dy by dz. It is that simple, guys. It's not super complicated. Apply a chain rule for neural network. So now when we perform the backward pass, we're going to take some partial derivative for this. And I'm going to just move this around a little bit here. And the total error now we can compute here. And then we can, so as indicated here, so this is what the formula that I showed you earlier as well. And now we are computing this. So once we calculate this and compute this, so this is what we're going to run this. So this is the value that we're going to run through to get the higher accurate outcome from this. Okay, so now, okay, so you guys can either run through the book or I'll just show you. So basically, I'm just taking a toy data set here. It's not actual data set that I'm taking from a file or something like that. I'm just taking from a simple toy data set I'm creating here and then just adding a cluster here. I'm assigning some random values to this. And I'm taking a cluster 1 and another cluster. And I'm just creating a toy data set here. And just when I print it out to show you what it has in terms of the cluster 1 and cluster 2 that I just created here. So that's what we have. So this is a cluster 1 in here, and this is a cluster 0 here. So basically, I'm going to create some weights for this, and then I'm going to do the forward propagation on this. As vectorized equations, and then I'm going to call a sigmoid function here for this, and I'm going to calculate the weights as we just saw it, and then I'm going to apply the backpropagation for this for all these data clusters that I just created, and these are the values that we saw for the chain rule calculation, and I'm just calculating and computing that over here for each cluster. And I'm applying this to the gradients, and then I'm gonna run through some, 10,000 episodes. To epsilon is a learning rate for a neural network, so that we're gonna have a higher accuracy. So I'm gonna create an epsilon learning rate as 1 here, and I'm just looping through this for each episode for all the gradients with the backprop function that I just created here. I'm gonna pass these weights here. And I'm just going to visualize this. So basically, this is the visualization of the neural network before the learning weight update. And so this is the visualization of neural network after learning weight update. So the error has been minimized now. And so now we can see that basically the learning weight update. This is how it's going to look like. So, I have given more explanation in the book for you to understand each step. I'm just showing the code here, but what I've written out. But you can also check the explanation of each step by step, like a cookbook, cookbook style I've written so that you can see that and understand each step, what we are accomplishing here. Okay. So now, as I told you that, so we're also going to take a look at $1 billion algorithm today, which is the singular value decomposition. So this is why this is called $1 billion algorithm. So everything that we have been seeing in terms of all the top technological companies in the world, like, well, for example, I'm going to take like Amazon or Netflix. They leverage the singular value decomposition, and it could be as heavy as it can get. And so you can see that how much you can scale with this particular singular value decomposition. We can build any type of recommendation systems for text mining, or we can run this for any company like Amazon, Netflix, and all of them there. And this has been there from the beginning. Like, was more of a mathematical application at that time, and then later it has been now scaled heavily to a number of industries. Even for example, like you go for eBay, also is leveraging reinforcement learning, and they also have singular value decomposition for recommending a product to the customers. And similarly, Amazon, like if you go and purchase a book, it knows that you bought this book and there is another book that you would like to purchase, maybe something with similar content, or has the topics that are covered in the earlier books. So something like that, it can recommend you when you're going for any product that you purchase on Amazon. You get such recommendations. So I'm just basically trying to here show you that whether this holds good or not. But again, you may have a question here that. So a lot of people ask me the same question in every conference. Okay, we're going through linear algebra and we are applying, taking some sample data matrices and showing you the RHS, LHS, all good. So they're saying, can we apply this to a neural network? Take these data matrix numbers here, whatever we are assigning, and can we apply to a neural network? And instead of running through, linear algebra here, can we run it in a neural network? This is the common question I receive all the time, but that's why I want to explain. See, basically, the singular value decomposition is a simple mathematical application for linear algebra. So if you want to apply for neural network, you could, but again, what I have seen in all the cases where this has been applied is like, if you are optimizing a neural network, you want to improve the throughput of a neural network, you want to speed up a neural network, accelerate that, then yes, you can certainly leverage this SVD, or what you call the singular value decomposition to the neural network, but not like the way that we have just went through the backprop calculation of a neural network. You're not going to create matrices for that purpose, because the way this calculation occurs is not exactly the way that neural networks function. So you can apply for optimization of a neural network, but not create a neural network itself and assign these weights. Any questions, further questions? Because this is very common question I get from every conference I go to. So that's why I'm asking if you have any further questions before we get started onto this. But again, I'm going to wind up quickly, another 10 to 15 minutes. But I'm going to go through this for now. And so basically, as we see here, the singular decomposition is basically a fundamental theorem, and where we have, so we're going to create a matrix, and we're going to assign some random values to it. And then, so basically, we're going to represent a few things here. So for example, the U, we're going to, it's an orthogonal n by n matrix. And the sigma is basically a diagonal matrix of size n by p matrix. And V is an orthogonal matrix of size p by p. And V of T is simply a transpose of the matrix, which is an orthogonal P by P matrix. So these are the representations of, so again, how much you can apply this, the way that industries are applying today are mainly on the natural language processing and text mining. So that's what you can see people are applying. So hashtags are word concurrences, words as rows, hashtags as columns. So everything works as a matrix here. It's not going to be like, something that you're applying as, um, like a neural network. It's not going to be like a neural network. It's going to be more like a matrix. So you can take words as rows and hashtags as columns, and you can also take the embedding of hashtags by the words they co-occur with. And then you can also take the embedding of words by the hashtag they co-occur with. So everything is going to be created as a vector mathematically, and then you're going to process that through. But to see that, we're going to just go through a smaller example here, but the actual examples of how to apply this in a natural language processing itself, you can find it in my book. There are more advanced data sets and things that we can leverage to apply this, that you can see that. But for this particular purpose of the conference, I'm going to just take a very simple example. So that I'm just going to take, I'm just going to create a rank 2 tensor here. And again, what is a rank 1 tensor? So that I have covered another session earlier, but that is not what we're covering today on tensor calculations. But I'm just gonna tell you is basically a rank 2 tensor is like, of a size 3/2, for example. So it will be of a data type of 32-bit single precision floating point, and the singular value decomposition is the most effective for matrices with high stability. Compared to eigen decomposition. So a number of applications leverage this. And so I'm just going to create, so I'm going to write this up in TensorFlow here. This is not going to be PyTorch nor Python. It'll be TensorFlow application here. So I just created rank 2 tensor here. And I'm just creating a TF constant, and I'm going to assign some random values as a constant to this particular rank 2 tensor here. And I'm just going to print it out. So what are the values I created as basically as rows? These are the rows, and these are the columns. So that's what we are seeing here. So for this little matrix X for the SPD computation, this is what we're going to have. And again, as I told earlier, that TensorFlow has a lot of built-in functions here, as opposed to Python, that we have some functions, but we may not have some functions. But we can leverage the TF lin alg dot SPD. So basically, a TF dot linear algebra SPD is a function for computing the singular value decomposition of the data matrix. The function primarily takes the input argument of the tensor full matrices, compute UV, and name of the function returns the values as SUV. So we just apply to it, and it's going to return everything to us. So I'm also explaining what are the input parameters for this function, and what are the computing parameters, and what are the return parameters here. So you can take a look at this and see how we can leverage. There is also a numpy function in the recent times, and notice that was updated with numpy.lin alg SPD, but then the calculation is much simpler in TensorFlow. Here, you just simply pass them, and then you get the return parameter. There's a little bit more processing involved with Python. There's a manual computation is required as well. But for now, we're going to go with this particular TensorFlow, and we just create a few matrices here, the diag D, orthog U, orthog V, and then the transpose. So basically, those are the matrices that we are creating, and it's saying that we are going to apply the TF lin alg SPD to the rank 2 tensor. We just created it, and we're going to just switch on the full matrices as true. We're also going to switch on the compute UV as true as well. And we're going to just simply print it after that. So it's as simple as that. We just pass these values, and it's going to give us our SPD that we just created, and then it's also going to compute the diagonal matrix for this. And these are the values computed for the diagonal matrix. And also going to compute the orthogonal matrix U for this. And it's also going to compute the transport of matrix V of size V to the power of T, which is a V transpose T. So that's the value we are getting here. Now we're gonna attempt to reconstruct this original matrix from the D and sigma of U and V. So we see how this particular values are going to be transposed to matrix V and see whether the LHS is RHS or not. So now we're gonna take the ortho U and then we're gonna pass these values that we obtained from the earlier computation. And then we just print the orthogonal matrix U, and that gives us the orthogonal matrix U. And we're gonna take the diag as a TF constant and pass the earlier values that we computed, and that gives us the diagonal matrix of D. And we're gonna compute the matrix V transposed as V transpose of T, and that will give us the matrix V here. So now SVD proof here is basically this is what we got here, which is 1, 2, 3. So it's exactly the same as the LHS earlier we have. So we are just reconstructing it with this logic to see whether the transpose is true or not, whether the SVD is true or not, is working or not. So basically it works. So the predictor worked, and it has actually computed the singular value decomposition. So this is now how much you can scale up. So you can scale up to any extent here. So if I go to Python, you can take a NLTK library of natural language processing and apply and create your words and create as rows, and maybe you can create hashtags as your columns and keywords or anything like that. And you can compute like any number of pages or any number of looks. So that will scan through the whole list of, for example, Amazon will have to go through every item and compute this text mining and come to a conclusion as to what would be the recommended. So you can build a whole recommendation system yourself when you scale this up to, but the purpose of this is not to actually, go and show you the full scalability of the purpose here is to go through the concepts to understand. So the scaling up is not, so like, for example, you're writing a SQL statement in your Python, or you're writing in MS SQL or Oracle or any other systematic databases. So you basically have to write a query, how you write the query, and then you can add any number of where conditions, or you can query any number of tables. You can inner join them, outer join them, so on and so forth. Similarly, I'm just showing the concepts here for you so that you can now scale it up to any application that you would like to apply. So basically, that is it for now. And we can, have some questions here, and then so we can go through, because there's a call at 12 p.m. for me. So I just would like to see if you have any questions, and we can go through that. Any questions? Any questions? You can find a lot of articles on Medium, and you can find that. Also, I thank the host, Amelia and Bimal as well, for bringing me onto this conference here. I appreciate for having me. Any questions? So I take that as no questions. So if we have any other questions, you can always reach out on LinkedIn and send a question, and I'll be able to respond to you. You can reach out anytime on LinkedIn for any further questions. All right, then. I put a question here. Okay, so there's some question here. Yeah, LinkedIn. LinkedIn is okay. So LinkedIn is, that's the LinkedIn. Oh, how can we talk about type answer? Okay, so that's the LinkedIn that I just shared here as well. Okay, you can always send this. Okay, here also you can put, okay, Yeah. So here is the LinkedIn, and you can reach out with any questions, and certainly we'll be able to connect and talk about it. And for now, I'll have to join another call, and appreciate all of you joining today, and I will connect again then.